So I want to today very quickly finish our discussion about the containers, and most likely I may not use up all the time, but let's see how it goes. So A3 is out and A4 is in April, okay, and Word.io follow up is via office hours. Okay, so I just wanted to try to wrap up some of this. We've seen containers to be basically built on 3 or 4 primitives. We've seen a whole bunch of them already. And we've not seen one last one, which is what I want to talk about today. So chroot and image files really were capturing application dependencies, namespaces were doing isolation of object views or resource views, and C groups was actually doing isolation of resource allocation, right? So how many objects or resources does every group get, right? So for example, we did do an example of C groups with a memory hog, right, where we tried to add a new process into a C group, which was basically thrashing on memory, and we changed some parameters of it and showed that it affects that process, right? So basically, so to generalize the idea of a C group, for example, you can do, if you have the memory, if you're dealing with memory, you can have a C group, or you can have 2 different C group called student and faculty, for example. Assign 99% of resources here, 1% here, right? And processes that belong to these groups will get partitioned according to that resource views, right? And you can subdivide this further if you want, and things like that, right? And basically the hierarchical restrictions remain within the subtree, right? So that's what C groups is used for. So the last part of the story is built on 2 notions of what are called capabilities and secure computing, right? And this is really, I think there's a clause called escape the container or something like that, right? Or minimize the attack surface. Okay, so really this is coming from the motivation of, if you have a namespace or a container that's executing, you want to restrict. So we have said that we want this notion of a restriction around the container and what the container can do, right? So one set of story that we have evolved is you can't see other processes, other namespaces, and you'll only get resources that we assign you to do. But the container itself is a continuously executing entity, and it has a common interface with all the other elements that are executing on that system, right? So the first 2, 1 and 2, right, or even 3, right? So the file system view, or the root file system and the namespace and the C group are only robust as the system call interface that is used to implement these interfaces, right? So because entities within these namespaces and C groups are continuously executing, and they have the same system call interface as everything else that has been used to set up this environment, they are sharing a common attack surface, right, or a common interface. And if any of that interface gets compromised, then all of the 3 that are listed above can get compromised, right? So for example, if you somehow can mount a new file system, or run chroot and change your root file system to something else, or add yourself to somebody else's namespace, right? Because we've seen that all of these are basically system calls, right? So for example, if you want to create a new namespace, you use unshare. If you want to switch your namespace, you use setns. If you want to change, either you do chroot or you do mount, So all of these are essentially getting into situations where end of the day you're calling a system call. And if these system calls allow execution entities within a container to do whatever they want, then you will end up running systems which can break all these three first primitives that we are building this container on, right? So one of the bigger primitives that is being used to restrict what containers can effectively do or correctly do is through these capabilities and what is called secure computing, right? So these are also independent axes in Linux which are being built and available either slightly earlier or simultaneously with the development of namespaces and C groups within the Linux subsystem at least, right? So I'm going to try and tell you what these do, and then we can see some examples of what they are doing and how they are trying to restrict elements, right? So for example, you may also do other kinds of things, right? So if you are a container and if you have been assigned an IP address, can you as a container change your IP address, right? And what does that mean? Every machine has a routing table which is being updated using IP tables and things like that. So should a container be able to change the routing table of that container, right, or of that machine? Because when you run IP table as a user process, right, you're eventually making system calls to affect the networking state in the kernel so that the forwarding gets changed for all packets that are coming in or going out, right? So that is the kind of crux of the problem that we want to also have control on. Otherwise, containers can do whatever they want to, right? That's not how we want to work with this. So these are two different notions of control that Linux and other OSs also provide with slightly different names. So this is called seccomp and what are called capabilities, right? So traditionally we have what we call the admin or the super user and a regular user, if you will, right? So if you want to do any particular action, you have to have a certain amount of privileges, right? So there are other versions of these privileges which also intersect with files and things like that, but this is execution level privilege, not just file access, open, read, write privilege, right? So for example, if you want to reassign an IP address, you cannot be maybe you can be a regular user unless explicitly allowed to do so, right? So capabilities are mechanisms to provide a larger or a bigger, or maybe I should call a varied set of privileges per process. So for example, whether this particular process can open a socket or not, whether this process has enough privileges to reset the networking properties associated with this machine, right? So for example, can you reconfigure the IP address or not, right? So there is a long list of capabilities. So what Linux has done essentially is moved this binary version of admin versus root to a whole bunch of what it calls capabilities which are associated with a certain action. And if you have the capability, you can perform that action, right? So that's the idea of what a capability means. And these capabilities are associated to every process and inherited by child processes as they go along, right? So I'll show you a list. There's a long list of such capabilities, and by default, all processes that come in inherit capabilities from their parent processes, and you can add or drop new capabilities as you go along when you set up and execute these processes. Yes.
So what is the difference between admin and root? Like both are performing the same action.
Admin and root. Yeah. So there's some. So there's some parlance difference and some actions that are different. So I think the root user might be slightly more privileged than admin, and I don't know what that exactly translates to in terms of some 2% or 3% difference in what these actions are. But for our current purpose, we can treat them equal. But I'll probably look it up and tell you exactly what that difference is. Yeah. APAMA, yeah.
So it's for access.
Yeah.
I think it's similar to this. So how does it do this?
Yeah. So there are other hardened versions of Linux, for example, right? So SE Linux or AppArmor, right? And usually they will use some version of this. So there will be a wrapper around some such primitive on top of which will allow things to happen, right? And I'll talk about seccomp, which is probably what they end up using, which is slightly even finer than what capabilities allows it to, right? But yeah, they have to depend on such OS facilities, right? And they use these capabilities. Right? I mean, these primitives, the capabilities primitive and the seccomp primitive, right? So in fact, capabilities are embedded in, I'll show you an example also of this, embedded in Linux source code. Which means that if you open up the implementation of some function or a system call or any other code in the kernel, you will see a if condition saying something like that. So if the current execution entity doesn't have these capabilities, do not do whatever you are supposed to do, right? So these are very implementation centric changes in the Linux kernel, right? So for example, what does it mean to not allow a socket to be created? Then wherever is the socket system call, you will have to make a check, right? And where that check happens is dependent on how you are implementing that socket system call, right? So if you go through the Linux source code, you will find there are different points in the source code where different capabilities are being checked to allow whether a certain action can be performed by this process or not, right? And I'll show you some examples of that as well, right? So that's the idea of capabilities. The intersection, of course, with a containerization format, for example, is to work with. So, for example, Docker can work with these capabilities by saying whichever container it is starting off with will be associated with a bunch of capabilities, right? So, whenever Docker starts, it associates a whole bunch of capabilities with that container process, and then that container or any process that is spawned by that by the container elements are associated with those capabilities, and they can only do a bunch of things that are being allowed for those processes to work with. And I'll show you an example of that as well. Seccomp is a similar idea, which is basically called secure computing. But this is essentially a system call filter, right, which has a few modes, which is strict or what's called a filter mode. So these are the modes that it runs in. The strict mode, I think, allows only 4 system calls or 4 or 5 system calls, I think, which are, I think, open, read, write, exit, and I think one more, I don't know which one that is. And this other mode, which is called the filter mode, is a customizable whitelist and blacklist. So you can create a list of system calls that you want to allow. You can create a bunch of system calls which you don't want to allow, right? And you can associate this profile, right? And I think the question that was being asked earlier about AppArmor or SE Linux. So you can associate what's called a profile with a process, and that profile gets attached to a process, which basically means whatever this process runs will be evaluated against that profile, and that profile is basically a list, and essentially a list of whitelisted and blacklisted system calls. So whatever the process does is basically going to go through this filter, and that filter will then take an action based on whether it should pass through that call or it should reject it, right? And many wrappers which are hardening the OS or the OS usage, like AppArmor and ACLinux, use a combination of these techniques, right, to allow different profiles of what users belong to. And if you want like 5 tiers of users and you want to associate what each user can do, they have to translate into some such combination of capabilities and secure computing profiles to allow them or disallow them about what they should be doing, right? So for example, if you say a user cannot create new directories, right? If that's what you want to do, you need to capture or set appropriate filters so that these actions cannot be taken, right? So in fact, this system call, the seccomp system call filter, not only works on system call type, but also works on system call arguments, right? So you can let a system call through with a certain set type of flags, but if a system call is called with a certain type of other flags, you can say no, I'm not going to allow you to do this. So for example, you can set a filter to read an existing file but not create a new file, right? Because the flags that come in for creating a new file are different from flags that come in if the file already exists, right? So for example, you can say O_create is not allowed. So you can process arguments as well and put filters on top of it, right? So compared to capabilities, this is a much more customizable or a programmable layer where you can customize what kind of filters can be applied for what kind of system call actions that can be taken, right? So in fact, with seccomp, the filter is applied as soon as the system call is made, right? So your system call may not even go through if it's not allowed, whereas in capabilities, all system calls are made. They land up in the kernel, and some kernel code is checking whether you should allow it to do these actions or not, and wherever the checks are basically hard coded, right? So they are in your implementation, whereas here you can do a little bit of more programming or leeway around what kind of filtering you want to do, right? So this is essentially, so BPF is also, so if I should extend this, so a seccomp is basically implemented via what's called a BPF program, and we'll talk about BPF separately. BPF is what's called Berkeley packet filter, but no longer. So BPF is another primitive in Linux which is in spirit similar to what we've seen so far, the Linux kernel modules, which allow us to extend kernel capabilities, but BPF is a slightly more robust version of kernel modules, in the sense that BPF programs get verified and then they can be attached to hook points so that you can actually get the program can be executed on an event, right? You don't have to. So for example, in a kernel module, you have to embed the kernel module in the kernel's runtime somewhere, right? So that you can get control. So the BPF program is slightly more customizable again, where you can write custom programs which get verified to make sure that they won't break the kernel, because the kernel module can possibly break the kernel anyway, right? Because you are part of the kernel. But extensions to the kernel which are verified and are triggered on events is what BPF provides, and seccomp is really riding on this infrastructure. We will probably look at a separate class in which we will look at BPF itself, because BPF is also being used heavily in the data center world for doing what's called offload processing, right? So a lot of OS interjection needs to happen before applications see data for whatever they have to do, right? So one big story of what's happening is people are pushing application logic into eBPF programs. So because eBPF programs run as part of the kernel, so for example, one of the things that it was originally used for was for doing packet filtering. So for every packet or every network packet that comes in, suppose you want to discard that packet for whatever reason. The packet has to go through the networking layer in the kernel, end up in the user space. The user space then looks at the packet and discards it, right? So if you want to discard something, it's much better to discard it quickly, right? Because otherwise you're spending all of this time at different layers to worry about it. So the packet filtering technique allowed to do that in the sense that whenever a packet came in, you could attach a custom logic for the packet processing before it got processed any further in the network stack to say whether this packet is worthwhile to looking at it at all or not. And if not, drop it very close to the source, right? So what does very close to the source mean? Very close to the source means that as soon as the packet is DMA'd into the kernel and the OS receives an interrupt for processing it, the interrupt handler currently kicks it into the conventional stack of network processing. So you can interject it, and that interjection can be a custom program. And you can say on Mondays drop every alternate packet, on Tuesdays drop every third packet, whatever your logic is, right? So that customizable logic can be inserted into this hook, and this hook is a packet reception hook. So as long as a packet is received, that hook point is reached and your program gets called, right? So a lot of work has been going on to offload custom application logic in data centers, or this whole story of what offload means for data center processing, and BPF is a big part of that story currently. But for SecComp, the same framework is used, but it is used to basically filter system calls. So whenever you make a system call, what's going to happen is you're going to transition from user mode to kernel mode, and you're going to try and jump to the IDT where this is going to be handled. But before that, the system call gets dispatched, the SecComp eBPF program gets called. And in that eBPF program, the context of that call is embedded, which is basically the system call details, and then your program can do whatever it wants to do. Right? So SecComp is really trying to galvanize the BPF framework to set up these filters. Right? And Docker and other mechanisms which enable containerization ride heavily on both of these techniques. Right? So for example, Docker has a default profile, a default SecComp profile that it attaches to every Docker container that comes up. And basically it's a whitelist of all the system calls that it allows, and everything that's not in the whitelist is automatically blacklisted, right? So those containers will not be able to make those system calls, or they will just return an error or things like that, right? So I want to show you a bunch of, so this, I'll come back to this if needed. Yes?
Linux capabilities in SecComp are like alternate of each other.
So there are two different subsystems within Linux, and they are different. Right, so capabilities is a slightly coarser version of SecComp, and SecComp is a slightly more programmable version, right? So for example, if you want to say, as I said, make a filter based on some arguments of what a system call is making, you don't have that level of control in capabilities. But if you want to do some action, so for example, you want to disallow creation of sockets, or you don't want to mount a file system, allow mounting a file system, you could do them both in capabilities and SecComp. Right? So you can do some similar actions in both these primitives. Right? So they were and are still two different parallel primitives in the Linux subsystem, and both of them exist.
Both are used together. Right?
Both are used together.
Docker uses both of them.
Yes.
I mean, SecComp is little complex to implement. Right?
Yeah.
And
Yeah.
it's easier to implement that.
Yes. Capabilities.
So for the coarser setting, Docker will use the capabilities.
Yeah.
And SecComp for the
Yeah. So I think it also depends. So there is no. So for example, as I said, if you want a certain set of users to not create directories, there is no direct primitive that you can probably use. Right? So you'll have to set up a bunch of rules around it for that thing to happen. Or you have to say if there are a bunch of users of a certain kind, you want this capability to happen. right? So then you have to have probably both of them in play to be able to establish what is the actual requirement that you want. You may not have one-to-one. So there's some simple requirements that are one-to-one, right? So for example, I'll show you a bunch of examples which says do not allow writing to a system, writing to a file, which means you can just disable the write system call, right? Or disallow network connections going out, right? So there's a capability called, I think, sys_net_raw, which basically says do not allow any network connections to open, right? But if you want to do let socket call happen, but it should happen only on some particular port, then you may have to use a seccomp filter to work with it.
How is it implemented? Means when system call happens, it is going to check whether this is allowed in the capability list or not, and then it will, if it is allowed, then only it will progress to actual system call.
No, I think in the execution sequence, the seccomp filter will be applied first, and then it will. So with seccomp, you will, as soon as the system call is made, the BPF program will be issued to check whether the filter will allow the system call to pass through or not. So once the system call pass through, in the system call implementation, there might be a capabilities check that may happen because that's embedded in the implementation of the system call source. So let me show you one or two examples of that, right? So before I do that, let me just complete writing this, saying what is there any other point there? Yeah, so I'll just say BPF program is invoked on each system call to apply filter. Let me just show you a few examples of this. First of all, just let me show you the list of capabilities. Okay, so this is anyway man capabilities, and there are a whole bunch of capabilities that can be associated with every user or every process, right? So for example, if you have the capability to change ownership, then you can arbitrarily change the identifiers associated with the process. If you have for example, so this one, so net admin, right? So if you have the capabilities of a net admin, you can perform various network related operations, right? So for example, you can do whatever, modify routing tables, clear statistics, set to promiscuous mode. So all you can do with a network interface card as admin user, if you have those capabilities, you can do that if you are running a process. So this is capability called net raw, and I think I'll show you an example using this, which says you can use raw or packet sockets and you can bind to any address for whatever. So there are basically a whole bunch of such capabilities, and this is a very long list, right? And basically the idea is, instead of breaking it up to go, no go, now you have a go, no go which is discretized in smaller chunks. You can have either all the writes, which looks like admin, or you can make smaller. So one common way to run this that Docker runs is, first it drops all the capabilities. So basically it starts a container with no capabilities at all, and it keeps adding the ones that it thinks that the container should get. Right? So for example, if the network, it should be able to communicate with the outside world, then you need that net raw capability. Right? So this, if your container doesn't have this capability called net raw, it will not be able to create sockets to communicate with the outside world. But you don't want it to be an admin, so it won't get the admin capabilities. So the usual technique of how containers set up is they drop all the capabilities first. So your container essentially cannot do anything at all, and then slowly keep adding the capabilities that you want the container to work with. Right? So this is a longer list, and it basically describes all the capabilities. But more interestingly, if you look at, so this is some arbit, slightly arbit, but let's hope it makes some sense. Let me open up this file. Yeah. So this is basically Okay, hold on. So this is basically a code which is trying to, show an example of loading and destroying modules, right? So whether a container should be able to install new kernel modules when it's running or not, right? Because once you install a kernel module, you're essentially part of the kernel. And once you're essentially part of the kernel, then you have the whole OS state available for you, including all the namespaces, all the C groups, and basically you're going to breach the sandbox that you're trying to build around the whole notion of CH root namespaces and C group. Right? So one important capability is whether you allow containers to load modules or not. Right? Of course, in a public setting, in a container as a service model, you would never want to do this. Right? But maybe in a private setup where you are just containerizing work for separation and where every container is every other container's friend, you may say, okay, containers can do whatever they want. Right? So it depends on what kind of a setup and what kind of a restriction that you want to provide. Right? And if you look at this, so this is the init module. So we'll go to init module if needed, but there was something in destroy which was easier to look at. Okay, so this is trying to find out whether you can, so this is part of init module, right? So whenever you're trying to run, load a module, you're going to call init module, and this is inside init module is trying to look at main init module, and main init module is essentially, so if init module is basically trying to check whether you have the capability to install a module or not, right? So if you look at the code, it says if not capable, cap underscore sys underscore module, return a permission error, right? And if you have that capability to install a module, then of course you will be allowed to go through, right? And as you say, this is embedded in kernel source code, right? So the implementation of the init module system call, or whatever, the function which is being used to initialize a module is actually checking for the capabilities explicitly, right? So in fact, as I showed, if I go back, so this is the system called init module, right? And it's got 3 parameters, whatever, third version of the definition, and here it actually is making this first check whether you can init this module or not, right? And the implementation of this is essentially checking very explicitly whether this process has that capability or not, right? So we can look at a few such different capabilities. So this, if you do a grep on cap underscore sys underscore in the Linux source file, you will see a bunch of such capabilities being tested for within different elements of the kernel code, right? And this is just one example here, of course.
Can we give specific capabilities to entire users, like any process that spawns from this user has this capability? For example, if I give a capsys module to a user, then it can do insmod without using sudo to load the modules.
So I think yes, you can do it for users as well. So if you look at capable, I think it looks for both users and processes. So I need to go a little deeper into this, but yeah, I think you can. So there has to be a little more. So user, for example, is really not a kernel feature. User is essentially maybe a OS feature, right?
It is right. So the kernel distinguishes the PIDs of the privileged, like the root users will run this 0 GID and something.
Yeah. So that's what. So I think from a pure kernel perspective, there is no notion of a user. The user wrapping has come up because it needs to do a whole bunch of other distinguished work for whatever some actions are. So I think you can probe users as well, right? So whatever I have worked with capabilities, I have done it at the process level, but I think there is a story of this which can be attached to users as well, right? And then everything that the user does. So for example, that call capable, right, is not checking on current, right? So I think it is flowing through a slightly deeper stack to come back and say whether this capability is valid or not. And I think the validity can be checked both for users or processes, right? I think by default it works with processes. I should check that and come back, but I think it works with users as well, right? So in fact, let me.
How can we modify the capability of the process?
Yeah, I'll show you that. Yeah. So let me just check this. Yeah, so I think by default it's just processes, but I think it can be made to work with users in a particular manner. Right, so I'll check that and come back. So what I was showing was a simple kernel example of how this is playing out. So let me show, say how to associate capabilities with running processes. Right? So there's a whole bunch of tools. So I think there's a file called cat proc. So let me just do this. So the PID namespace for every process also stores the capabilities associated with that process. I forgot that. Anyway, we'll come to that, but we can just run this if you want. So you can find the capabilities associated with a current process or a current PID in a proc file. I forgot the directory of where it's exactly there, but it's an encoded bit sequence which lists all the capabilities that are associated with a process, right? And there's a bunch of utilities that can process this already. So either we can do it or we can just use the tool. So there is a tool set which can be downloaded, which is already available in most Linux distributions called, and in that one of the programs is this thing called getcaps, right? And getcaps can get the current capabilities of a process, right? So given any PID, it will list all the capabilities that are assigned to this process right now, right? So if you want to do something else, then you'll have to either add or drop capabilities to this process, right? So how do you do that? There's another tool called capsh, right? So that basically, so for example, you can do something like drop all, and you can add, right? So you can, whatever, you want to drop all capabilities of a process, or you can add all capabilities to a process or some capabilities to a process. Right? So let me try and I think I'd set up there was a simple example that I borrowed from somewhere else. So this is basically trying to see whether you can so this is basically dropping all capabilities and trying to ping some arbitrary address. So let me change that to a better address. Let's say 10.129.2.27. Yeah. So if you look at this, when this command runs, it eventually fails by saying socket operation not permitted.
So, but for which process was it done? How is it mentioned?
No. So this is capsh is basically a shell which is saying start. So capsh, that program capsh is a utility which is trying to run a new program in a shell with these capabilities. Right? So capsh is the utility which is setting it up. But how do you set up a new process for execution with the capabilities of what capsh is doing as an integrated script essentially, right? So capsh drops all capabilities and then tries to run a program, right? And that program is basically ping -c and attempt four times trying to ping this IP address. So whenever you're trying to ping an IP address, you're trying to create a new ICMP socket or a new socket and send a bunch of ICMP packets on it, waiting for some ICMP reply. But since we have no capabilities to do this, this is just going to fail, right? But you can update this by running minus drop all add and add net underscore what is that, sys underscore net underscore raw, right? I think that was the capability, right? So if you look at the previous thing, the current capabilities were this. When you dropped the capabilities, the bounding set became null, which is the effective set of capabilities under which this process is running. So now we are going to try and drop all but add sys underscore net underscore raw, and hopefully that capability will be enough to run this program. So क्या हो गया, कुछ तो गड़बड़ हो गया क्या? I think I got the name of that capability wrong. Cap underscore sys ना, क्या है उसका नाम? Cap net wrong, sorry. अच्छा वो sys तो I'm confusing with SIGCOMP, sorry. Okay, so let's try and see if we rerun this one. Okay. I'm still getting it wrong. Cap underscore net underscore raw. Okay. Cap underscore net underscore raw. Yeah. ये प्रिंट की वजह से नहीं. अच्छा ये माइनस माइनस नीचे नहीं.
Add is not double add, or add is not there.
It's not add, sorry, my bad, it's caps. Caps is equal to unable to intercept. What am I doing wrong here? Re-execute with argument, the remaining argument when bash. Okay, set UID group ch root print drop caps equal to set caps as per. Oh yeah, okay, this is just I think called net raw. Sorry. Okay. Sorry. Keep.
equal to cap.
Keep. Oh. No, but that's a bit number. I don't know which bit to say. I think it is caps equal to. I'll just look it up. How to add capabilities via campus. No. Okay. Cap underscore is there, yeah, okay. No. Okay, I'm messing up the cap sh syntax for some reason. Cap sh double quotes. Double quote. Cap underscore net underscore raw. Is that it? Okay. No. Sorry?
Cap underscore net underscore raw plus E. Inside the
Plus EP.
EIP.
EIP. नहीं ऐसा नहीं. Oh God, this is supposed to be slightly more dramatic than what I'm hoping for. हाँ, इधर एग्जाम्पल होना चाहिए इसका नहीं? Without just EP. Okay, let's try something slightly simple. Okay, good. You're pinging something, right? So that works. So that's what cap sh minus add cap net admin. That's what the. Okay, let's do net admin. Doesn't matter.
Cap, you don't have to write row.
Sorry?
Only cap, not row.
Only cap?
Remove row.
Remove drop? No, if you
Only cap, then it will show.
no, if you drop, then everything is happy. If you drop, then everything is happy. No problem. Oh yeah, add, right? I think it was add. No. Maybe my version of this is as per cap from text. Okay, now what I don't know what cap from text is. Okay. How about do that? Okay, I'll cap underscore net underscore net. Okay, yeah, see this just yeah, so EIP. So there is a user also here, so I think that also works. So single quote say okay, so clearly I've messed up that
So can you justify once to put hyphen keep equal to 1 and the previous stays the same?
yeah, sorry.
Plus EP one stays the same and just put hyphen keep equal to 1. That's very
You can process it, but
Row one is removing what we are setting caps. You can see here the current is your caps.
yeah,
But row is
yeah, but the bounding set also has to have that. Okay, I'll fix that. I think I thought I had figured this out for some reason, but okay, good. What is the proper syntax of cap sh minus cap? Okay, let's see what that is. Oops, what happened? Cop from text. Okay, okay. But what will it return? We have to know what it returns. Okay. Oh God. Okay. Now really try this. You can try it. Okay, I'll figure that out and send that. But believe me that you can drop and add capabilities, right? For now. Yeah. So maybe I'll show you something slightly more workable or dramatic in another sense. So this is, so that was capabilities, right? So that was capabilities where we can add and drop capabilities according to the list of capabilities that are available. This is an example of seccomp, slightly more involved. Let me try and see if I can explain this better. So this is a C program which is basically trying to, I don't think you can guess, let me just switch this. View, window, edit, no, shell, export, edit background color, okay, good. So this is really using a internally, so this is a user program, right? So this is a user program which is trying to set the filters to be associated with this program to run with it, and all the child processes of this will work with this filter as well, right? So this is run through a special system call called PRCTL, which is basically trying to enable a whole bunch of process control actions, right? So that's what's called the PRCTL system call. And all this is trying to do is install the filter and then run a bunch of commands, right? And we'll see what that install does. So after you install the filter, there are a whole bunch of system calls obviously. So printf will make a bunch of system calls, write will make a bunch of system calls, open will make a bunch of system calls, close will make a bunch of system calls, right? So let's look at this. No, that's just a function up here, right? So this is just a function. Okay, so the main things that the install is trying to do is on line number 38, right? On line number 38, we are trying to call this system call called PRCTL, right? Which is trying to set the seccomp, right? And the second variable is trying to set the seccomp in what's called the filter mode, right? So as I said, there are two modes for seccomp to work with, strict and filter. So in strict mode, it will just basically zip out all the system calls and allow only 4 or 5 of them. So this is basically saying I'm trying to control behavior of this process with the seccomp primitives. I want to run seccomp in filter mode, and I'm going to attach a third parameter which is called the program, right? So it's an address to a memory location, and at that address is the program that I want to run, which encodes the filtering that has to happen for this process. Right? That's what that system call is trying to do, right? So basically what we need to now provide is that program which does the filtering, right? So this is basically trying to set up the kernel execution flow to say that once this process makes a system call, the seccomp mode is enabled, it's enabled in filter mode, so run this program, right? And the program itself is here. Right, so the program itself has to be what I said earlier, a BPF program, right, or a Berkeley packet filter program, and which has to be written in what's called a BPF bytecode, which is then interpreted or just in time interpreted by the kernel to execute when the BPF program gets invoked, right? And that's a different stream of how BPF programs are set up and run, and we'll come to the generalization of BPF. But essentially what we want to do is provide a program which allows us what has to be done in BPF syntax, right? Or the way, so BPF has its own ISA in some sense, right? And that ISA is what we need to follow to establish that program. So the way BPF works is that bytecode has a particular format, and that bytecode is just in time translated whenever a program has to be executed with the kernel. But when you write BPF programs, they get translated into this bytecode. So this program has to have that bytecode specification, right? So what this example is trying to do is basically build a filter, which is basically a bunch of sequence of commands, and give a address to that program, right? So if you look at this, so this program is basically a bunch of macros, right? All of these things are basically a bunch of macros which are provided by the BPF library to convert into a bytecode, right? So you can write generic programs in Python or C and run them through what's called a BCC, so BPF cross compiler, right, which will compile your C program to bytecode. Or you can, if for smaller programs we are just using these hash defines or these macros directly, and these macros will generate the equivalent bytecode for us, right? So what the bytecodes here are doing are basically validating the architecture. So for example, you have to say what architecture are you running this program on. So if it's an x86 architecture that you want to run this program on, then this program should actually be running on an x86 architecture whenever it gets executed. Then you are trying to examine the system call, right, whatever that system call number is. So these are all macros, right, and we can open them and see what that actually call means, what that call actually means. But what your program wants to do is examine the architecture, get the system call, and then there's a whole bunch of macros which are allowing a bunch of system calls. So for whatever your macro number is, for your system call number is, if it is in this allow list, so this is basically like a if then else, right? So if this allow, if this allow, if this allow, if this allow, if none of this, then this system call is basically not allowed. And if you don't fit in any of these allow list categories, the action that you want to take is you can either just return from the system call saying return with error, or in this case they are trying to basically just kill the process, right? So that's the last, so line number 29, which is basically saying kill process, right? So this is, as I said, just like pseudocode, right? Behind this is a macro which is generating the bytecode for each of these actions, right? But that bytecode is according to the eBPF syntax, right? And it has some 3, 4, so it is like a 4 tuple that you can specify for every instruction. You can say what you can do on an action, what you do on a jump, and things like that, and a return value, right? So there's that bytecode encodes a BPF instruction which has 4 parts to it, and each of these macros are basically doing that encode.
And we are passing the array of those instructions.
So this is just a sequence of instructions, right? This is an array. So this is just instruction 1, instruction 2, instruction 3, instruction 4, right? So that's basically a list of instructions in your program. So that's the first instruction, there's a second instruction, third, right? And if you look at this, we are passing prog. So this is basically in a structure called filter, and this filter is part of this socket fprog called prog, which is what we are passing to our PRCTL, right? So basically we are sending a bunch of instructions and number of instructions in that program in one structure, and that structure is passed to PRCTL saying this is where the program exists.
For each process, are we applying the filters? How is it?
No, this is for the process that's executing. This whole process, yeah. And any child process that will be created from this process. So this in main you called install syscall filter. So after this function is called, this filter is applicable to this process. Yeah. Yeah. So this program is applicable to this process after that call install. Right?
Can we have the hierarchy of this? Let's say process 1 actually has some kind of program that process actually calls some another process that has another program which is there in the filters.
Yeah, but the seccomp criteria is that filters can only get tight. You can't loosen up filters.
Okay.
So child processes can't say I want a bigger system call subset. So you can only make stricter calls.
So we can add the
You can add more filters, but you can't loosen up the filters in child processes.
So like for Docker, it will be given like install syscall filter will be called inside the Docker itself. So
Yeah, Docker. So the Docker setup program, which is trying to set up a new process with a new namespace, will create this and fork everything else from it. Yeah.
also we need to restrict that capacity or the system call before once the container is created, because if someone is allowed to do that system call, then essentially it can change the allowed list.
Yeah. So you will have to create. This has to be the orchestrator process, right? Yeah. So you have to set up everything and then change the process control that is allowed for the processes that are going to get created from. That's true. Yeah. So this actually, unfortunately, I think I can't compile this program on my box because I don't have a BPF installed there. But what this is basically trying to do is allow, sig return, exit, read, write, and open. And if you run this program, this line number 57, which is close, right, is a disallowed system call, right? And if you hit close, the program basically will terminate, right? Because close is not an allowed system call to be made, right?
So the kill process instruction there means that if a disallowed call is called during the kill.
Right. So kill underscore process is basically a BPF macro, which is saying if you hit this instruction, your process is going to die, right? And the way we are using it is basically if you make a system call which is not in the allowed list, the default action is that you'll execute kill process, which is basically going to kill the process. So close is in the black list; it's not on the white list. So it doesn't go through any of that, and so you can substitute close with any other system call other than read, write, exit, whatever you added in the whitelist. It will still, the program will still get killed. And in this case, this close is a close on an FD, right? It's not an exit, but you're just trying to close a file descriptor, but your program is going to get exited. Right? It's going to get killed.
Validate architecture core will run.
Sorry?
The validate architecture core will run on every system.
Where will the?
Validate architecture.
That will run on every system call. So this is a program that is going to be executed for every system call. Right? So the filter or the program is for every system call. So yeah, so there is a trade-off, right? So if you are making a whole bunch of system calls, you are actually interjecting new code to check for every system call correctness, or basically applying a filter for every system call.
Why anybody wants to validate architecture?
Sorry?
Why anyone wants to validate architecture on every system code?
Well, yeah, so I think Ishan is worried about this. Why is this happening? Line number 14, right? So BPF, for example, is very concerned about what you can run in kernel mode, right? So this is actually a user program. I mean, we are writing this program in user space, and we are going to stick it into the kernel. So the BPF doesn't want to run in the kernel anything that it's not supposed to run, right? So for example, if there is an instruction set which is not x86 compatible, but you still execute it on x86, which of course you can do all of that because it's all basically hex encoding. But what does that mean for the CPU, right? So for example, BPF is not concerned if you are moving values between two registers, right? So move A comma B, which is for example in x86 language C8, 48, 78, right? So some encoding. But now if that in a different ISA means something else and you just let it run, you are actually going to run some different set of instructions on the CPU. Right? So it is very, very touchy about what you want to run on your CPU. So I think for one of those things, it has to make sure that the program basically works correctly.
So why not if BPF includes it by default itself? We have to explicitly declare it inside the filter.
No. So for example, that architecture. So this is basically just bytecode. Eventually, this bytecode has to get converted to that architecture. So if you say that I am PowerPC, so bytecode will generate PowerPC instructions. But if you are actually executing on x86, then your PowerPC sequence of hex numbers are being executed on x86 CPU, and they may do whatever, and that encoding of instructions will not work. So for example, PowerPC move is say 68, x86 move is 58, right? So you are actually running on an x86 machine, but you say that the architecture of this program is PowerPC. So the bytecode that will get converted for actual execution will generate 68, but you are running x86. So 68 will get generated, and 68 in x86 may not be move, it may be reboot or whatever, some random stuff like that, right? So you don't want such things to happen. So what you are converting to as a architecture from this bytecode and what is the actual architecture that you are running on should eventually match, right? And that, I think it will do a check for that on every program instruction that's actually being run. Maybe there is an optimization to save that somehow, but I think that's really where it's coming from. So if you run this, unfortunately on my program, on my machine, I think libbpf, the library is not installed and it won't run, right? So I think I have a very slightly older machine that I'm trying to run this on, but I'm sure that if I'll leave this code somewhere, and if you download it, you can play around with it to make sure that this filter takes effect, right? So eventually we'll also see more generalized framework of how to write BPF programs themselves, but the story of BPF is really of how you are encoding this program right now here, and then pushing it via PRCTL to control how the process works from a system call for filter perspective. I had a few examples of how Docker may be using it. Let me see if I can bring that up. So let me write this. So the way Docker can use this is through a bunch of Docker run commands that it can add on to, and similar to what we were trying to do with capsh, Docker run, right, so similar to what we were trying to do with capsh, Docker can take a whole bunch of commands as well. So Docker run can do a cap drop all and cap add, net underscore raw and things like that. And it will internally use capsh to set up that environment for the container that's actually going to run. Docker can also do things like seccomp. I think it says some seccomp underscore profile. Let me just see what that is.
Capsh, if you only define cap flag and don't define throw flag, then your program will have only capabilities that you define in cap.
Looks like it, yeah, looks like it. Right. So there is another parameter with Docker run called seccomp, and you can specify a JSON file which encodes the listing of all the filters that you want to apply, right? And internally it will take, so that is a standard specification, a standard format specification. Docker can interpret that specification and convert it into the seccomp policy program that we were trying to use as a dummy program, right? So it will read a JSON file with all the whitelisted filters as a profile, convert it into a PRCTL program, and then push it into the container's root process or PID1 that is going to execute, so that everything after that gets attached to that filter, right? So Docker already supports these primitives via its own orchestration logic, right? So all the small versions of the tools, utilities and the programs that I was trying to demonstrate are embedded within Docker in a more generalized sense, right? And they can work with all these capabilities in them, right? So if you run any standard container, I think there's a way to probe Docker as a admin and also understand what capabilities you have provided to the container that you just started. I think Docker info should do that, or Docker capability. I think there's a certain capability probe flag as well. I don't remember what that is. But for any container that you start, you can probe it to understand what capabilities you have assigned as well. Right? Okay, so I think that's really the story of the container primitives. We'll hopefully bring it all together in A3. I don't think we are doing seccomp and capabilities in A3 per se, but you're welcome to do it, or in the open-ended version of A4, maybe you can extend A3 with some notion of capabilities and seccomp filters as well. But we are trying to bring this together in A3. We probably will not do anything with filters there, but all the other parts are getting aligned in A3. So by the time we finish doing A3, we'll probably have our own Docker Lite variant, which will have a small Docker file like specification, which can generate a small overlay image file and set up network for that container, and deploy applications if you want to, right? So that's what we are trying to get into A3. Hopefully this covers most of the background and primitive foundations for that, and we will take it as it goes, because A3 is already out. We can also hold a separate session if you want. I think A3 is a little bit tricky in the sense it's a lot of it is script oriented, but you have to make sure that you're following this correct sequence, correct syntax and things like that, right? So if you're having difficulty with that, we'll have a separate session on that as well.
Can we have a session on EBF implementation?
EBPF implementation, yeah. So we are planning a separate tutorial to just understand what eBPF is trying to do and come up with a bunch of examples around it. So we are intersecting with eBPF right now with seccomp, but we'll do a more generalized version of eBPF from the perspective of how it intersects with cloud and data. So it's really being, so eBPF currently is, as I said, it provides programmable filtering capabilities, right? So it is being used in various ways. So one big way it is being used is for offloading networking logic. So instead of moving all packets through the networking stack into the application and doing a whole bunch of things, one big idea is to move network logic into eBPF programs and make it as close to, make it quicker, higher efficiency and throughput as close to the network interface card. It can also be extended through all kind of other kernel subsystems, like we've seen system call filtering. So a lot of people have been using it for measurements, telemetry, for all kinds of system profiles, right? And they are also building in more extensions for doing customizable scheduling and things like that. But there is a large framework of how you can actually write these programs correctly and the whole library around it. So we will do a tutorial of exposing what that means. Maybe we may not be able to actually deploy large scale eBPF programs, but we'll certainly go through the API, the process, and there are a bunch of live eBPF projects that are underway within our group. You're welcome to come by and talk to any of us, or maybe I will make a small summary of all those projects, and at some point if you're interested we can look at more on that as well. Yeah, but currently there's a lot of excitement about what eBPF is doing with conventional system subsystems, right? So kernel subsystems, and definitely we will have something on it before we wind up for the class. Okay, so we'll stop for today, and I'm lagging behind some notes update, but I'll have all of them updated by the end of the day today, right? Thanks.